And I would like to present today the renewable carbon concept and the initiative. But first, a few slides on Nova Institute. Or something here. Okay, yeah. Nova Institute was founded in '94. We have an international team of 40 scientists, and our main topic is the support, the transition, the smart transition to renewable carbon. I will explain in a few minutes what it means in detail. You see already on the right side, renewable carbon, circular economy, and this is based on bio-based, CO2-based, and recycling. But more details later. The institute itself has four focus areas: is technology and markets, where we do market research and technology scouting. Lars will present what we did on chemical recycling. Sustainability, that means sustainability assessments and life cycle assessments, specific on chemicals and plastics. Communication, Bo told already about the problems in the plastic area, so it's also a communication problem. So we're supporting many companies finding the right communication for new products launch. And finally, economy and policy. We're following in detail the policy in Brussels and worldwide. This is not the topic today, but if you look to the Single-Use Plastic Directive and so on, there's a lot to understand, to discuss, and sometimes also to influence. Our customers are from all industrial sectors. You see on the left-hand side big brands we're working for. In the middle, chemical industry, automotive industry, other consulting companies. But our main focus is the chemical industry. As you see here, from the biggest one to the smallest one, they're all looking to new solutions for the future, and we try to support them with market information, technology, sustainability, and those issues. One important point of Nova are the reports, and you will see some more details in my presentation and the presentation from Lars. We have just published several new reports on bio-based polymers, on CO2-based polymers. I will show 2 slides today on recycling, and you will see some examples. If you want to have a further close look to it, you can go to bio-base.eu/reports. You can always find also summaries. Another service which could be very important for you all here is the news portal with about 26,000 reports. You can type the name of your company in, and you will be surprised what we all have about your company already in the system. It's free to use, free to send us press releases, and it's the biggest news system on chemicals and plastics in the world. So please join. And one of the last information here is the International Director for Bio-based Businesses, where we have 115 companies showing what they can offer for the market. It's free to have a profile here, and also free to have access to the profiles. And we have in some years up to 50,000 downloads because the clients can look for food contact, or they can look for specific lubricants, or there's very specific, you can look which companies can offer the services. Now I come to renewable carbon concept. You know Ursula von der Leyen, European Commission, Green Deal, and reducing emissions by at least 55% to 2030. A few months ago, this target was even more strict. It was before, it was 40%, and now it is 55%. And this is not easy to achieve this target. And because one of the very important backgrounds of the whole initiative is, where are the carbon emissions coming from? What is the real reason for our greenhouse gas emissions? And if you look to the IPCC report and make a little other clustering as usual, then you will see that 80% of the greenhouse gas emissions are directly related to fossil carbon from the ground. So we're taking oil, crude oil, natural gas, or coal from the ground and bringing this carbon in the technosphere and atmosphere. And this has to be stopped as soon as possible because this is 80% of the impact. You can ask yourself, what are the other 20%? The other 20% coming mainly from land use changes. So if you destroy rainforest or you switch from grassland to agricultural land, then you have also emissions. These are the other 20%. But the main point is additional fossil carbon. In the energy sector, there are clear strategies in Sweden, in Denmark, everywhere about wind, not so much solar in the north, in the south more solar industry, hydrogen coming from using water for electricity, for example. There are many ways in the energy sector how to decarbonize, but the industry has to go beyond renewable energy, because if you go to our sector, chemicals and plastics, you need carbon. Yeah, you cannot decarbonize your polymers and plastics. So we think that the equivalent to decarbonization in the energy sector is a transition to renewable carbon in the chemical and material industries, and how we can substitute the fossil carbon from the ground by other carbon feedstocks. And this is the key of the initiative, renewable carbon. And I will explain a little bit further what it means. But first, we did for the European Commission a report, which will be published in the next month, on the carbon demand, because it's very interesting to see when we decarbonize the energy sector, what is the leftover long-lasting carbon demand from our industries. The picture you see here is the first time ever we did all this in carbon. And this is how it looks today. You have biomass and fossil carbon mainly. CO2 is a very small part so far. Recycling, as you see, also a small share. And the biomass is going mainly to food and feed, but also to chemicals and energy. And the fossil carbon going mainly to energy, and also about 10% in the chemical sector, chemical material sector. I'm not allowed to show the results for 2050 so far because the publication is not out, but we made different scenarios for 2050 to identify which carbon demand comes from chemicals and materials and how this can be covered. Yeah, to have a quick summary of so far, decarbonization is a good strategy for the energy sector, but no issue for chemicals and materials. There is a lasting need for carbon. This is often not well known for the public. 80% from the greenhouse gas emission are directly related to this additional fossil carbon. The key challenge is to replace the demand for fossil carbon, and those alternative carbon sources are biomass, CO2 and recycling, and we call them together renewable carbon. So we have also a nice clear definition. Renewable carbon entails all carbon sources that avoid or substitute the use of any additional fossil carbon from the geosphere. Renewable carbon can come from the atmosphere, direct CO2 utilization, biosphere, biomass, or technosphere, but not from the geosphere. And renewable carbon circulates between the biosphere, atmosphere, and technosphere, creating a carbon circular economy. This is a meanwhile very famous poster we developed the last years, where how a sustainable future can look like. On the left-hand side, you see solar, wind, and hydro as an energy storage and carrier hydrogen. And with this, you can cover till 2050 almost all energy demands. On the right-hand side, you see the material part, chemicals and materials. They are fed by CO2, biomass, and recycling. The CO2 needs hydrogen, green hydrogen, to get C utilized as a CO2. This is the connection between the energy world and the material world. And so we can keep producing all kinds of products, but not using additional fossil carbon. The only pathway to the energy sector are the carbon-containing fuels. And this is mainly kerosene. Kerosene is not easy to replace by hydrogen or electric batteries. Yeah, so if you need carbon, we have two choices. We have the fossil carbon on the right-hand side, crude oil, natural gas, or coal. We should stop this. And on the other side, we have the three: biomass regrown, CO2 recaptures, and recycling recycled. Yeah, I don't think I have to go into too many details here. All kinds of biomass are here accepted: first, second generation, side streams, bio-waste. For CO2, we have point sources like power plants or industry, or also fermentation factories, or we have direct air capture from the atmosphere. In the technical sphere, we mean all kinds of plastics and other organic chemical products from the technical sphere we can use in mechanical or chemical recycling. This is the next point in the next presentations. If we look at strategy in detail, the most important thing is here that today we see a lot of fight and competition between bio-based, CO2-based, and recycling, and don't fight brother wars. The winner will only be fossil carbons. We have to share and win and bring the three solutions together. The best thing would be also have a joint policy on the three carbon sources, but this is a dream we're working on. If you see the plastic overview of how it looks today, we have for the fossil-based plastics about 360-380 million ton production worldwide. The growth rate is 3 to 4% per year. Bio-based, we have 4 million tons. I show only one slide here, not the topic today. 4 million tons. Recycled, we have worldwide 10 times more, 20 to 40 million tons, mainly mechanical today. And in CO2-based plastics, we have already production of 850,000 tons. Surprising for you, but I'll show some details in the next slides. This is one of the possible futures of the polymer sector. You see the production volume 2018. And then if the growth rates will continue like it was the last 10, 15 years, we will come up in 2050 with 1.2 billion tons of plastics. Let's also show we need to solve problems like microplastics and others, and also the image, because this cannot happen in the wrong social and policy framework. But if it would continue, and this year, the last year, this year will show the same trend, then we have really a big amount. And this can be covered about 60% by recycling. Of course, chemical recycling is an important part here, by bio-based and by CO2-based. And if you look to the numbers here, what areas you need and so on, it's really possible to do this in a sustainable framework. And we go in a little bit more detail here from our reports. This is the bio-based polymer production capacity is today a little bit higher than 4 million, and it will in 5 years be around 5 million. And there are 17 commercial used bio-based polymers on the market. But you can receive the slides later, and also the new report is released today, and so we can also get for the press new numbers, because what's happening now is really exciting. We saw in the last years in the bio-based area growth rates like in the fossil-based, so not additional shares. The main reason was no political support. But we see now a new trend. Now we see very new data here, and much higher growth rates, up to 8% for polymers, and the building blocks even 11%. So we see really a new trend for this in the next 5 years. And the reason is not the political framework, but the reason is that brands really looking for non-fossil solutions. One example, if you look to Unilever has said till 2035, they're not accepting any fossil carbon in their detergents, and they're just making pressure on their supply chain that they're not accepting fossil-based detergents. That's a big step. And we see this in a lot of other brands too, and this speeding up the demand for those new solutions. When we look to the CO2-based polymers, this picture shows the pathways from left-hand side CO2, different processes, chemocatalytic and fermentation and others. And then you see on the right-hand side some specific polymers you can mainly make from CO2, but you see also polyethylene, polypropylene, PET. So finally, we are CO2, hydrogen, Fischer-Tropsch, and naphtha, for example, or methanol, you can produce all plastics, polymers and plastics we know today, you can all produce also from CO2. It's just a question of the costs for renewable energy. And you have some areas today where you have renewable energy for 2-3 cents a kilowatt hour. And here you can really start using CO2 also for polymers. And another report also published today gives all details on this pathways. On recycling, Lars will show this, so I have only one slide. So chemical recycling is another way to bring plastics back to as feedstock. Now my last slides are on the initiative. The Renewable Carbon Initiative was founded and launched in September 2020, so it's very young, 4 months old only. And the aim is, of course, to support and speed up the transition from fossil carbon to renewable carbon for all organic chemicals and materials. And companies joining it have a lot of benefits. I don't know. I don't think so. If you have questions, I will go here in details. But I think there are mainly 2 things that are attracting companies to join the initiative. The one is they really love this concept of renewable carbon, because many companies working in bio-based, in CO2-based, and in recycling, and they want a joint strategy. And so for many companies, our initiative is just the right way to go, because they're anyway going in this direction. So these companies like that we spread this message around, that we have a lot of press releases, contact to the commission, and spread the message around. I just showed to you. The other part, companies joining it want to have the network. They want to really build up value chains. They want to have solutions. They want to have access to CO2-based polyethylene, to use cooking oil-based polyethylene, also those things. So their hope in this network of companies, they can really create new process and value chains. And here you see the member of the initiative so far. So we have all the time, the question here, whether you can receive the presentation, for sure, you can get the full presentation. Here you have the companies. We have, every month we have 3-4 new members. You see here huge companies like DuPont, Unilever, Covestro, Lenzing from the textile area, Henkel, Neste, Uniper. On the other hand, you see also small startups here, BioBTX and other small companies, Lanzatech, W from Israel. We have now the new members from Asia coming soon. And we have also partners with other initiatives, Global CO2 Initiative, Go PHA, Textile Exchange, and we're waiting for another big names here. Here's a question. I can just look whether it fits now. As end my presentation, then I go to the questions. So this is, I think, is more successful as we expected. And if a company presents today, you want to join, the first step is have a one-hour meeting with me, that we can discuss all the details. So what are your benefits, what you have to deliver. And after this discussion, many companies starting the process of joining the initiative. And my target is to have in 1 year 100 companies, so that we have really a strong initiative, which have also a voice in Brussels, in Berlin, in Copenhagen, in Stockholm, wherever it's needed. We have also a lot of personal supporters, nearly 180, which are really often very famous experts in their areas, but they could sometimes not yet convince their companies to join as member. But this is also a huge community, and we will also create soon a renewable carbon community with a few hundred companies with very modern social community software to really network and start also projects together. And one meeting point for all people interested in these areas are our next conference, the Cellulose Fiber Conference is next week. CO2, Chemicals and Fuels is in March. And then we have created the new conference, Renewable Material Conference, 3 days. And here we're combining the best solutions on the market on bio, best solutions from CO2, and best solutions from chemical recycling. So the brands are so excited about this conference that they can go at one place, seeing all sustainable materials. The first day will be on chemicals, the second on polymers, the third on plastics and composite material. And this is our renewable material tree, showing the future, 3 sources of carbon, renewable carbon, and all the nice products we love in our world made from non-fossil carbon. Thank you for your attention. Last picture show the heads of our departments, and thanks for your attention, and I'm happy to have some questions.
Thank you, Michael. Very interesting. I have a question first. What is the reaction from the EU when you come up with this discussion about renewable carbon? What do you meet?
That's a very interesting, good question. What we see at the moment is that big companies, NGOs, and the European Commission are watching very closely what we're doing. So if I met them and I asked, do you know our initiative? Oh yeah, Michael, we know everything. We have all the slides. And so they are very, very aware of it. But if you send to 40, 50 experts in the Commission such information, they're absorbing it, but they're normally not reacting, because reacting would mean a lot of additional work. And this is only if you really want to do that. So what we now plan is the following. We're just preparing a basic background paper where we show why renewable carbon is a key indicator for chemical and plastic industry for sustainability. And with this paper will be ready in 4 weeks. Then we will have a specific meeting with the Commission, DG Environment and others to present this strategy. But we first need to read this background paper. Everybody is saying that we need land use, biodiversity, 1,000 criteria, but we have good reasons to put renewable carbon in the front. And this concept needs some basic sources and argumentation, and we are just doing it. And after we have this, we will have meetings with the Commission.
What kind of support do you expect or hope for from the EU?
Yeah, we hope that it will be part of the Green Deal, because if you look to the Green Deal, there's nothing real about chemical and plastics. If you look to the chemical strategy of the Commission, it's only on toxicity. So there is no vision in Brussels and also in other member states, no vision how the plastic and chemical sector can develop in a sustainable future industry. And the Green Deal is not talking, there's no one word on replacing fossil carbon in chemistry and plastics. And so we hope that we can finally add this important aspect to the Green Deal and other activities. And this is the main target.
All right. Shall I pick up a couple of questions that has been put to you here? We have one from anonymous attendee. He or she asks, our supplier of polypropylene claims 100% price premium to replace with the bio-based on a mass balance approach. They also say the price will increase further due to shortage on the biochemical market. Is this a fair call?
Yeah, the good thing is that we can make polypropylene from chemical recycling, we can do it from CO2, and we can do it from biomass, and they're very different pathways. So we have a lot of options, and of course it will be more expensive. The time that in the petrochemical fossil area, carbon is extremely cheap, and all alternative carbon sources for the future will be never again so cheap as in the fossil age. Yeah, but we pay a high price for fossil carbon, climate change. So it's a very high price, and if we're not accepting this anymore, yes, we have to pay more for our carbon. But on the other hand, you are all plastic experts. I think one problem of plastic is that they are too cheap. If a plastic have a higher value, society would also handle plastics in a different way. So I think plastic will become more expensive in the future, but this is perhaps not a bad news, because it's for everything the same game.
Okay. Another question from Heidi Foucault. Do you have reasons to believe that the increase in bioplastics has an LCA analysis as basis? Is it verified that the projects are really environmentally friendly?
LCA has for the methodology a wide range of options and assumptions and so on. So the LCA is not a fixed system, but a very flexible system. And it's depending on how to make the golden scope in detail. And we see that the Joint Research Center is just publishing, I think the next month, rules how to make a good assessment of biopolymers in LCA. We will see what's happening there. But in general, when we see, sometimes we also say, if you only look to LCA, sometimes you cannot see the forest for all the trees. And it's a truth, 80% from the greenhouse gas emissions coming from fossil carbon. So there is no way to go away from fossil carbon. And we say in our institute, when companies are coming, they say, please compare fossil bio CO2 and recycling. I say, no, we don't compare this because fossil is no option. We compare bio CO2 and recycling. These are the future options, but fossil is no go. And it would be the same, you say, oh, let's go on with coal plants, solar and wind are not so nice as we think. No, we don't doing it. We have decided to go to renewable energy, and the same decision has to be here to go to renewable carbon. But back to your question, we're just doing, for example, a huge LCA on PEF, this new polymer compared to PET. It's a European project, Avantium. This is peer-reviewed, it will be published soon. And there you can see in a very complex and detailed LCA that there is a chance for bio-based polymers, even today, to be really better than fossil polymers. But it's also depending on the whole energy system. So if you have a 100% renewable energy system, this comparison will also change. And what we're doing in LCA is we're doing a lot of LCAs per year for a lot of clients. We also make a LCA from today and also look how the results would change if we go to 2030, 2050. And then we see normally that if a bio-based polymer is not completely convincing today, if you take the advantage, the improvement in agriculture system, improvement in the energy system, then they can easily win the game 2030, 2050. And we're looking for solutions for the future. So I think we should always have LCA from today and a future LCA with very good solid assumptions.
Okay. Another question from Magnus Klügel. How does carbon monoxide-based plastics like PK fit into this?
When I talk about CO2, it's only a simplification. Of course, CO2 and CO are both important. If you look to the first CO2-based polyethylene bottle produced from Total in France, based on Lanzatec ethylene, ethanol ethylene, they are using the emissions from the steel plants, syngas, and there you have CO2, CO, and hydrogen. So in most cases, we have only CO2, but in certain industrial emissions, we have always CO2 and CO, and this, of course, is fully part of the picture.
All right. I have another question for myself. I just picked up the figures that came today about the development for the bioplastics with 8%. Seems to be an all-time high, and it's double the figures for fossil-based plastics. How shall we understand this?
Yeah, it's the only driver for this are the brands. It's really, and it is an interesting experience over the last 10 years. If you implement some CO2 reduction logic in your company, it's really after 5-10 years, it really works. And we work with so many big companies now, and all the companies ask me, Michael, how we can get away from fossil carbon. Yeah, what we want to do in the energy sector is clear. That's no problem. But we need solutions. And this is really a new trend. This trend is since about 1 year. That there's real demand for non-fossil solutions, and we call it renewable carbon solutions. And this is driving it. And the good thing is that the brands can just put pressure on the supply chain. So if they say, L'Oréal want to have this CO2-based PE bottle, yeah? So L'Oréal is saying, okay, you cannot deliver? Okay, I take another supplier. So there is a new coming pressure on the supplier to make really the transfer to renewable carbon. And this is the driver and not policy. If policy would understand this, and this is another point in Brussels, if policy would understand that there is really driving from the big companies, they could easily support the development and make it even not 8%, but 20-30% growth. But the policy sector has always problems with chemicals and plastics. They think more they need bans and restrictions, but they're not developing a vision for them. And this is also what we want to try to do. I think chemical and plastic industry is so important for the future. We need a new image. We need another carbon source. We need a complete new framework. And if I'm in discussion with plastic enemies, happens often today, I ask them always the question, if you go hiking, look to yourself. You are dressed up from the whole body with high performance polymers. Yeah, the shoes, your socks, everything is from high performance. Why you fight against plastics? And then normally they keep quiet 5-10 minutes because they start thinking about it. Yeah, we need plastics, but we need another carbon source for them to make them really sustainable.
Last question for you, then we have to continue. From another anonymous attendee, what are your thoughts about fiber reinforced plastics from a recycling perspective?
This is, of course, a very specific question.
Yes.
The fibers are, of course, natural fibers, cellulose fibers are, of course, fully part of this initiative, for sure. And we have the Nova, I cannot tell the details, but Nova is doing with important big companies from Sweden and Finland, just projects on recycling of biocomposites and WPC. So there is a lot to do in this area, and we organizing these activities, but I cannot tell you more details about it here.
No. But there is a company in Finland who is actually producing biodegradable fiberglass also. So that's quite interesting.
Yeah, but you can be careful. You can never say that glass fiber are biodegradable. Biodegradable means producing CO2. And if you cut down glass fibers, it will never get CO2. So they can talk about deconstruction of the material, but it's never biodegradable. And we have to be very careful with these definitions and terms. Otherwise, we're only confusing the market and the clients.
All right, Michael, thank you very much for your participants here. I think we have to continue now, and I will hand over to Lars Krause, also from Nova Institute, and he will tell us, give us an update about the chemical recycling today, because there's been a lot of talking around the chemical recycling as an alternative for the future. I mean, we have the mechanical recycling, we have composting and all that, and but I think we will never reach a level where we can recycle everything. But maybe chemical recycling, or not maybe, but chemical recycling seems to be a very interesting step towards much more recycling, actually. So, Lars, please, the screen is yours.
So hello everybody, and welcome to my talk, in which I want to give you a brief overview about our recently published report with the title Chemical Recycling: Status, Trends and Challenges. This report will cover several aspects around the topic of chemical recycling. So it will also cover the technologies, the sustainability, policy and key players. In today's talk, I want to focus a little bit stronger on the technologies, but I will also cover several other aspects. Before we go into the topic of chemical recycling, we need to take a small excursion through the waste generation and treatment in Europe, as well as the quite ambitious recycling quotas which were set up for the European Union. So in Europe, approximately 30 million tons of plastic waste are produced, and 29 million tons of this waste is collected, leaving approximately 1 million tons of plastic waste that is leaked into the environment. From the collected plastic waste, approximately 43% is recycled, 25% is going into landfill, and 32% is going into incineration for the energy recovery. And the European Union has set up quite ambitious recycling quotas. So until 2030, it's planned to recycle approximately 70% of all packaging materials and 55% for all plastics in this packaging materials. And the European Green Deal goes a step further. So it's communicated that until 2030, all packaging materials should be either recyclable or reusable. And as a long-term goal, until 2050, the European Union will be climate neutral. So the question is now, okay, how we achieve these ambitions. So in general, we have 5 options available. So this is the prevention, the reduce, reuse, recycling, as well as alternative feedstocks. So let's go through the different options. So the prevention is economically and ecologically sensible for only a few applications because there's nearly no alternative available for most of the applications. So the reason is the overall performance and the properties of plastics. Here we have the density and strength. So plastics are representing very strong, but at the same time, very lightweight materials. Another plus on the plus side is the general processing properties of plastics. So plastics can be easily formed and reshaped via heat application. And then we have the large sector of specialty and high performance materials, as Michael already told us. So we have a range of plastic products with tailored properties. And in general, plastics have the better performance than other materials for the most sustainability criteria. Then we have the options of reduce and reuse. So of course we can reduce the amount of plastic waste via intelligent product design. So less plastic waste will be generated then. And in case of reuse, we have the options to keep the plastic longer in the loop. But it can't fully prevent the generation of waste. So it's more or less a delayed waste generation. And now we come to the 3 other options, which are also a part of our renewable carbon initiative. So first of all, we have the alternative and renewable feedstocks, so bio-based or CO2-based feedstocks. These feedstocks are preventing the introduction of fossil carbon into the cycle, but this is not a direct solution for the waste. So it's only a solution for the emission of more greenhouse gases, the introduction of fossil carbon into the cycle. And then we have the last option, the recycling. So this is the only option or the direct option for waste to largely prevent the landfill or incineration. Recycling keeps the plastics in the loop, and we have various options available. However, the recycling requires a full established circular economy across the value chain. Let's keep in mind, without recycling, the life of a polymer would be very linear. So we have only limited options to treat the plastic waste. The options would be, in general, incineration and energy recovery or landfill. And these solutions are always coupled with either greenhouse gas emissions or the environmental pollution. If we now include every recycling option which are available in a complementary approach, we see that the life of a polymer can be really circular, and we have various options available for very different waste streams. And all these options together are able to reduce the greenhouse gas emissions as well as the environmental pollution. Let's go through the different recycling options we have, and let's start with mechanical recycling. So the ISO 15270 defines mechanical recycling as processing of plastic waste into secondary raw material or products without significantly changing the chemical structure of the material. Sorry. The mechanical recycling can be divided into the primary recycling and the secondary recycling. The primary recycling is more or less the in-plant recycling, and the secondary recycling is more or less the recycling of post-consumer products. The mechanical recycling have certain advantages. So it's very well-established technology, and the technology is characterized by its simplicity. However, we have some limitations. So the mechanical recycling is limited only to thermoplastics, and we need some kind of pure fractions. So for in-plant recycling, it's not that problematic, but for post-consumer products, it can become to a huge problem because the waste streams need to be pure. So we need one kind of polymer material, and it needs to be cleaned from other organics wastes and maybe also sorted according to color. So it can be a huge problem to recycle this very heterogeneous wastes. The other limitation would be that contaminations are not removed from the waste stream. And now we come to the chemical recycling. So if we want to show you a definition for the chemical recycling, we have a lot of different definitions available. They are partially contradicting to each other. And if you have a look on all the available definitions, we see that there are in general two different approaches. So we have one scientifically motivated approach and the more political approach. And here you see from ISO 15270 a more scientifically motivated approach. So here chemical recycling is defined as conversion to monomer or production of new raw materials by changing the chemical structure of plastics waste through cracking, gasification, or depolymerization, excluding energy recovery and incineration. So this definition would include different technologies such as Solvalysis, Pyrolysis, Gasification, and Enzymolysis. But it will exclude the technology Dissolution. So because here the chemical structure of the polymer itself remains unchanged. And this here is an example for a more politically motivated definition. So this was done by Chemical Recycling Europe. Here is chemical recycling described as any reprocessing technology that directly affects either the formulation of the polymeric waste or the polymer itself and converts them into chemical substances and or products, whether for the original or other purposes, excluding energy recovery. In this case, the dissolution would be included besides Solvalysis, Pyrolysis, Gasification, and Enzymolysis. And if we now include all these chemical recycling technologies together, we find some advantages over the mechanical recycling. So here we are not limited to thermoplastics only. So the only exception would be in this case the dissolution, but the other technologies are not limited to thermoplastics. We have no need of pure fractions, so they can be more heterogeneous in comparison to the mechanical recycling. Contaminations are also removed from the waste stream, and the material is characterized by its high quality. But we have also some limitations. The chemical recycling can be really complex. It is not that well established due to the lack of large-scale units. And we have some difficulties to prove the sustainability of the different technologies. Let's go through the different technologies, and let's start with the dissolution. With dissolution, a target polymer can be dissolved in a suitable solvent, and all the other components which are in the plastics, such as fillers, other polymers, additives, pigments, and so on, are not dissolved. So these components can easily be removed from the target polymer, for example, via filtrations. Then an anti-solvent can be added to the solution, and this initiates the precipitation of the target polymer. So the target polymer can then be removed from the solvent. It can be cleaned and dried. So in the end, you have a really pure polymer which you extracted from the plastic. The remaining solvent can also be recycled, for example, via distillation. The dissolution technology has several advantages. So on one hand, we have the selectivity for certain target polymers. We can address mixed and multi-layer material, and the output can be directly used. So in comparison to the Solvalysis, we don't need to make a repolymerization of the polymer. And toxic substances can also be removed from the waste stream. A disadvantage will be that we have some requirements on the composition of the input material. So to have an economically sensible process, of course, you need a certain amount of your target polymer you are addressing. And another disadvantage will be that you are limited on thermoplastics, and the solvents may also need to be purified after the process. In our report, we identified worldwide 6 technology providers for the dissolution, and they have already capacities of up to 8,000 tons per annum. Now we are coming to the Solvalysis. Here, in general, the process works as follows. So a target polymer can be depolymerized into its building units with a suitable solvent. So the building units would be monomers, dimers, or oligomers. And after this process, the monomers needs to be purified in order to be repolymerized into the polymer again. So here we have an additional step in comparison to the dissolution. Depending on the utilized solvent and mechanism, we can divide the Solvalysis into the alcoholysis, including glycolysis and methanolysis. And we have also the hydrolysis and ammonolysis. Here again, the advantages are very similar to the dissolution. So we have the selectivity for target polymers. We can process mixed and multi-layer material, and toxic substances can be removed from the waste stream. Disadvantage side is also a little bit similar. So here again, we have the requirements for the composition of the input material. So we need a certain amount of our target polymer. And the solvents also needs to be purified again. And here polyolefins and polystyrene cannot be processed with this technology. For the Solvalysis, we identified in our report 14 different technology providers with capacities of up to 10,800 tons per annum. With Pyrolysis, we can process really heterogeneous waste streams into different solids, gases, and liquids. This happens in presence of heat and absence of air. The products are secondary valuable materials or monomers of the polymers. So we can obtain from this process syngas, different liquids such as diesel, naphtha oils or monomers, but also waxes and char. A part of the needed energy for the process can also be obtained from the partial combustion of the feedstock. So it can also be provided by the feedstock itself. And on the advantage side of this process, we have that, a range of different input materials can be processed. So even plastic waste together with some bio-waste. We have a large spectrum of obtained products, and toxic substances can also be removed. But we have also some disadvantages. These are the high energy demand, the emission of pollutants. We have less selectivity for products. So on the one hand, the large spectrum can be an advantage, but it can also be a disadvantage, especially if you really want to obtain a special fraction of all these different products. Another disadvantage would be that the products often needs to be further processed or upgraded, and the process has a low tolerance for PVC. In our report, we identified 44 technology providers for pyrolysis with capacities of up to 38,000 tons per annum. The gasification is also able to process a very heterogeneous feedstock. This happens also again in presence of heat, but now also in presence with air and oxygen. And the product which is mainly obtained is syngas. Here we have again advantages. So the process is very robust regarding the input material. We have various applications for the process synthesis gas. And again, toxic substances can be removed from the waste stream. Disadvantages are the high energy demand due to the very high temperatures needed for this process. We have high pressures and also again the generation of pollutants. And a special case for the processing of plastic waste is here the higher tar contents, which you have also in your product. So if you want to utilize the obtained gas, you need this to consider if you want to use it in turbines or engines. And we have also a reduced caloric value of the product. In the report, we identified 8 different technology providers with capacities of up to 100,000 tons. And last but not least, another chemical recycling technology is the enzymolysis. So this covers the depolymerization via biocatalysts, so enzymes, microorganisms. The enzymes can be highly specific. So you have chemo, regio, inertio, and stereospecificity of the enzymes for the polymers. Overall, the process can be conducted under very mild conditions in comparison to the other technologies. So this process also works at room temperature and at nearly atmospheric pressures. Another advantage is the fine-tuning. So you have always the possibility to adapt your enzymes via enzyme and metabolic engineering to the process. However, the enzymolysis is rarely developed and currently under lab scale, and you have at the moment relatively slow turnover. Altogether, the technologies are suitable either as a recycling or as a recovery operation. The question, especially for the thermochemical processes, which have maybe higher energy demands, here the question is how they can justify their process as recycling operation, and how can this count into the recycling quota. One approach would be a life cycle assessment, and here we have different approaches available. So below you see 2 different approaches which were published by BASF. So in general, you can either compare, you see this on the left side, the process itself and the alternative. So here on the left side, you see how the pyrolysis is compared to the incineration regarding the greenhouse gas emissions. But you can also compare on the product side, so by comparing the production of fossil-based plastic with the production of chemically recycled plastics as another approach. Okay, to conclude with this slide, the general outcome of our report. On the right side, you see some statistics of the identified companies, which are explained greatly in detail in our report. So the blue bars are showing you the number of identified companies for each technology. And in orange lines, you see the already established maximum capacity of the technology. And here you can see that the thermochemical technologies are delivering at the moment on the market the highest capacities, and pyrolysis is the most dominant technology at the moment on the market. But this may change. And here you can also see that the Enzymolysis, for example, is still under an early development. And here we identified only one technology provider. On the left side, you see some citations from supporters and critics on the chemical recycling. And I think these citations are greatly give you an idea of the general outcome of the report. So the supporters say a modern sustainable plastics industry that fits into a circular economy cannot do without chemical recycling, since the targets set up in the EU plastic strategy will not be achievable without implementing chemical recycling technologies. However, supporters call for a clear policy framework from EU policymakers. Critics of chemical recycling refer to the low maturity of the technologies and the wide uncertainty range of existing assessments. Another overarching point of this criticism refers to gasification and pyrolysis, which could undermine meaningful activities towards the circular economy. And with the last 3 points, I want to conclude the outcome of our study. So the sector is characterized by great dynamics, high expectations, and investment interest. On the other side, we have great uncertainties and skepticism as how the new technologies should be evaluated and regulated. And in Europe, the chemical recycling sector is waiting for the start signal via clear political framework conditions. And with the last slide, I want to end my talk and give you some further information around the report, which can be accessed under bio-based EU/reports. And I want to thank you for your attention, and I'm open for discussion.
Okay, thank you, Lars. That was a lot of information. Yeah. But interesting. What would you say from your point of view? As far as I understand you, there is not one technique. It's not one size fits all, so to say. You have to choose. And the pyrolysis has the biggest staple in the diagram. Do you think the pyrolysis is the most interesting technique for the future, or?
So I think they are so every technology is interesting and important for the future. So it doesn't mean that pyrolysis is at the moment strong at the market. It's the most promising. This would be wrong. So as I already said, and the slide where I showed every recycling technology, this needs really to happen in a complementary approach. So it's very important that a waste stream, so when one technology is not able to process a certain waste stream or side stream, then maybe another technology can catch this up. So, and this would be the complementary approach. So I think even for the mechanical recycling, you have a lot of waste side streams which cannot be processed. And this would then go somewhere else. Maybe it's the pyrolysis or maybe another technology. And especially if you have multi-layer material, we don't need really to discuss about mechanical recycling. So then we have mechanical recycling with the Solvalysis and so on. So I think it's very important to communicate that a real circular economy would work only in a complementary approach.
So chemical recycling does not mean that we can stop sorting out different fractions in the plastic. We still need to have this sorting in some way before they go to pyrolysis or to chemical recycling, whatever. Am I right there, or do we need to sort out the plastic waste in different fractions and then decide what kind of chemical recycling that should be used for just that fraction?
Yeah, this is what we already do. So we already established a certain sorting system.
Of course.
But you really cannot sort out the different polymers if you have a multi-layer material, for example. So this would be impossible. And you will also have always municipal waste, which is always heterogeneous. And then you, of course, need a certain technology to address this. So it would also be unrealistically to accept that we improve the sorting system to a point where we only have pure streams. This wouldn't be possible.
So we should still continue to strive for much more monomaterial. That will make it much simpler.
This would also be an option, yeah.
Yes. You did show a lot of figures here. The total amount, what is the capacity of chemical recycling today if you look at your figures? You said it was 100,000 ton pyrolysis, I think. And what if you put them together, how much is it? You know that?
I think if I look at the graphics, I would say nearly 200,000.
175, yeah. Maybe 170.
Yes. Maybe so, but it really depends. So this are in this case I showed you only the maximum capacities. So there are also some companies, they are at the very beginning, of course. Yes. So it's difficult to sum this up for everyone. So some companies are still under development and can't tell you numbers. But this figure was important to show that there are already companies who can already provide this capacity, because in the discussions is many people are telling you, okay, this is not a real thing, so they are all under early development and can't deliver, but this is not really true. So there are some companies who are really well established and evolved in the last years, and we were also surprised by this impressive numbers. So what's already available, and if the policy would be a little bit more enabling in the future, I think this will further further improve the development at the moment. Because at the moment, I think, especially for the startups, they don't want to invest at the moment until the political framework is not clear.
No. What do you think about the political framework? Do you have any ideas there? Do you know anything?
Yeah, I think there's a lot of stuff to do. So especially to have a clear framework, and especially to address each technology in a fair way. And this is stuff which needs to be discussed also for the crediting system and all the LCAs which are around. So we need a clear framework how we can, or how the companies are able to operate.
Perhaps I can add one sentence to that, because it's a very important discussion, Bo. The question in the Commission is at the moment, we had a meeting with them last week, whether they will say that certain technologies in chemical recycling will count in the recycling quota, or whether it's an LCA-based system that we have to show that you are better than fossil virgin polymers, and then you will count. And this discussion is at the moment going on in the Commission, and the result is not easy to foresee, because many lobbyists from NGOs and chemical industry have a word here. But what will be decided finally has extreme impact on the investment.
Okay, but can we see a time frame instead of a framework? Can we see the time?
It will last in any case a few months, and then it go to the European Parliament, it go to the member states. So normally such a process takes half year or 1 year.
Okay. Lars, I have a handful of questions from the attendees here, so maybe let's go through them quickly here. It's Patricia Eisenberg who is asking, could you explain the role of catalyst in the chemical recycling technologies? Thanks. And she adds, and its impact in the cost of the processes.
Yeah, of course. So this would be too detailed for an overview. So I excluded the catalysts. So of course they play a very important role, especially if you want to invest. And in this case, you have a wide range of options for different catalysts. So if we are talking about catalytic cracking, Of course, you can, on the one hand, have very expensive catalysts and which cannot be reused or needs to be refreshed after the process. So this would be very high costs that need to be considered. But on the other hand, there are also some catalysts available, and I know some companies which are using them that are very cheap, and they don't need to refresh this catalyst. So this is a small investment then in this case for the company, and they say, okay, this works for us. So yeah, this is a very specific field, and of course needs to be elaborated how this fits together in a good model. Yeah.
All right. There is a question from Ulrika Persson. Would the materials done from chemical recycled plastics help to lower the carbon footprint compared with fossil sources?
Yeah, so in this case, in this slide, I tried to really show this, what potential we have. So in our study, we also summarized all the recent LCAs which were done. So the LCAs were done by partially by universities, but also from companies like BASF or INEOS. And in general, all the LCAs were able to really show that the emissions of greenhouse gases can be reduced. So the question here is, okay, do we have plants with a really high capacity to really prove this? So this is the only lacking thing at the moment. The LCAs are only makes some assumptions, but this really needs to be proven in the future. But I think in general, as every LCA we have seen at the moment, they showed a very promising picture. And yeah, and I think in the near future, this really needs to be proven with large-scale units.
Okay. Sreparna Das asks, how much does the fact that chemical recycled grades can be used in food contact application help its case to be favored?
Mm-hmm. Yeah, as an example, so with the technologies like Solvalysis or Pyrolysis, you're really able to produce plastics or chemical recycled plastics, which definitely have the potential to be used for food contact. And this recycled material definitely has can have a virgin quality. And even if not, you still have the possibility to have a certain barrier between your packaging and the food itself. So this is always an option. And yeah, this can also be considered, of course. But the potential is there. The question is, how good can this be proven? And the future will tell us. Yeah.
Okay. Emily asks, can you give examples of what kind of contaminations you can remove with the chemical process?
Mm-hmm. Yeah, in general, let's take the example of dissolution. So you really extract only the target polymer from the plastics, and you will leave every other component or you can separate every other component from the plastics. So you can get out every pigment or additive or filler or something else. So you can really remove this and separate this by nearly 100%, I would say.
Okay, let's go for the last question, then we must continue. It's from Peter Rasmussen, Suomen and company. In most LCAs, mechanical recycling give better CO2 savings than chemical recycling. Do you agree?
I would say it's possible, of course, but the question here is, do we really need to compare this? So does it really make sense? Because if you have a waste stream that cannot be mechanically recycled, So what would be the alternative? So in this case, the alternative would be maybe incineration. And here the comparison makes more sense than comparing this with the mechanical recycling. So it's always a question of your input stream and what you can process. Or you have multi-layer materials. Then we can't compare this with mechanical recycling.
Okay.
But it can be, of course, but the question is, makes it sense?
Okay, Lars, I think we have to continue. This was also almost all the questions I had there for you. Okay. So I think it's time for our next speaker, and that's Mr. René Backes from Badische Anilin- und Sodafabrik. I think it should be BASF, actually. One of the very big chemical companies in the world and one of the leading companies, I would say. And they are also working with chemical recycling, looking at that, but they do a lot of other things to be even more environmentally friendly. So René, you're going to tell us a little bit of the status right now. So the screen is yours. Welcome.
Thank you very much. I hope everything is okay with the audio. So I start to share my screen. Let's see how that works. So can you see my screen now? I hope so. Yes, perfect. I would like to talk today a little bit about ChemCycling and mass balance and how this is approached by our company. And as a matter of fact, the time is quite advanced. I separated my presentation into 3 parts. First is a very short introduction about BASF, what we do. And then if you want to understand how ChemCycling plays a role within BASF, you have to understand how we produce today. And then you can see a little bit more deeper into detail what these production from today means for challenges for the future. And that's my 3rd part of the presentation. So a very rough start with very rough figures about BASF. In 2019, we had roughly 60 billion euros in sales, with a little bit below 10% of EBIT of that. And we managed together with roughly 120,000 employees. Our company is very, very broad. We supply chemicals to almost all industries you can imagine. It starts from very crude raw materials, which we call petrochemicals, and it ends up with very fine chemicals we sell into agricultural solutions. So you find a very broad spectrum of products we have. Yes, from, let's say, normal basic chemicals until high performance chemicals. That's very short. If you need to want more information about BASF, please contact me later. We can share this. But if you want to understand how ChemCycling and mass balance approaches fit into BASF, you have to understand how we produce today. And before I start this, I start typically with our purpose, because we have one single purpose, which is overruling everything. It's like we create chemistry for a sustainable future. That means all our business decisions are connected to sustainability and sustainability evaluations. What does that mean? Just 2 or simple examples I have here with me. We want in the chemical industry to be recognized as action leader, thought and action leader in the area of sustainability. And with every our business decisions we are taking today, we would like to increase the role of sustainability. So for example, we would like to decouple our CO2 emissions from the organic growth we expect. And we also invest into cutting edge technologies to speed up this, for example, ChemCycling. And I would like to start with a very simple principle in chemicals and in chemical industry from the beginning that you get, let's say, all on one page. For us, it is important that we follow the energetic path. That means I have here on my slide deck, I have with me the 2 functions, oxygen content in our normal molecules and molecular size and molecular weight. Very simple speaking, we start in the down left corner with crude oil or natural gas. And what we do as a chemical industry is we introduce in first order, we introduce oxygen into crude oil. And then we derive out of that materials, polymers, and other functional materials, for example. So very important to understand is we start energy rich, we start with purified products, we increase functionality, and we try to do this with very simple reactions. And this is all leading down the energetic path. I will show you on the next slide. What you see here today is what we really do. We start with naphtha, which is 1 fraction of crude oil, or with natural gas on the below. And this is, I don't want you to remember this, but we follow from down to top with the products. We define chemical entities on the way between, and then we just start to functionalize these materials. So it's like from PTX, which is benzene, for example, we introduce oxygen to phenol, or for example, from propylene, we come to propylene oxide, and so on. So this is something how we work. We start from below and we grow up. And during this path, we are losing the intrinsic energy of the molecules they contain. So that's important for you to understand. We start really energy rich and we are losing the energy by producing polymers. And what you do not see on this screen is this is just the precursors of our polymers and our plastics we have. What you see is here, plastics and other chemical products come at the stage 3 or 4 after crude oil. So it's a long journey from crude oil until plastics. And if you remember the presentation of Lars, the volumes we're talking in ChemCycling, you get a real feeling for what is possible today and what not by remembering pyrolysis recycling volumes in Europe, for example, from plastics are about 15,000 to 20,000 tons today. And we are operating an integrated production site in Germany, in Ludwigshafen. Our demand of raw material naphtha is roughly 2 million tons per year. So it's a huge difference between what is today available and what we need to process. So just to give you a certain understanding what is going on here. Secondly, what we like to see is this is technology of recycling of chemicals, for example. It's a technology which is evolving, which is in its childhood phase today. So please give us a little patience to increase this. What I did not mention is that whenever you do a chemical reaction, you have side products, you have side energy, you have waste energy in these reactions. And what we are doing is we are using side products and waste energy to avoid greenhouse gas emissions and optimize our process. So this, what you see here, is totally optimized. Every side product is used as a new starting material, for example. So, and I would like to, how does it look in real? I have one picture with me that shows Ludwigshafen from the view from above. What you can see here is 5 kilometers long and 2 kilometers in width. And you see here, this is production site next to production site. So this is everything, let's say, based on fossil materials today. Yeah, not 100%, but let's say 90% is fossil materials here. And yes, I told you before, we are optimizing and we are looking into our emissions, into our greenhouse gas emissions. And what I have brought with me here today is what we achieved during the last 30 years. So some of you are young enough to remember that in 1990, we had these Kyoto Protocol and the conferences in Rio, where we started already at BASF to measure how much CO2 do we blow out, or how much greenhouse gases. And what I just want to show you on this is, like, we managed to reduce our greenhouse gas emissions since 1990. We managed to reduce this by roughly 50%. That means that, for example, we had 100 tons of CO2 emissions in that times, now we have 50. But you have to understand that in the same time of that, we doubled our output. So on that time, we have more than 100%, is roughly 104% of materials as output increase within Ludwigshafen, for example. So this is something like, yes, we already have reduced our carbon footprint today, and we would like to maintain our organic growth, but honestly saying, the low-hanging fruits of saving CO2 emissions or saving greenhouse gas emissions have been harvested. From now on, it's really going down to the bones. We have to do really in deep dive into where can we save CO2 emissions. So our next target until 2030 is at least to keep our CO2 output constant, and there's no way in the other way around. We have to reduce this in the future, and it's not a matter of that we have to reduce it, just a matter of when we have to reduce it, but it will be to be reduced. I showed you I showed you the Ludwigshafen site in the last picture. We are operating 6 of those production sites, all equal within raw material demand. And today we are investing into a 7th structure, into a 7th production site in south of China. And as you remember, we are consuming 2 million tons of naphtha every year alone in Ludwigshafen. This tremendous amount of raw material, today fossil raw material, has to be somehow compensated. So yes, this is a challenge, and let's see how we can manage in the next years. So that was basically how we produce. Let's see how can we move on into the future. A little bit about raw material change and the opportunities. It was nice to see this morning in the presentation of Osa that she was mentioning there is a willingness at the customer side. And yes, typically I separate my presentation here with like, I have 2 news for you, 1 good news and 1 bad news. And I will start with the good news. And the good news is, yes, the customers are there and they are demanding us. And even they are faster than legislation. So this is a very good sign. So I have just some examples. I would skip this. Be prepared to provide 100% greenhouse gas neutral products in the future, and in best case even have some carbon or greenhouse gas positive products which have a positive effect on the atmosphere. So this is what is something what I would like to say from the Nordic point of view for you is like, be aware it will be better from the customer side. Now to the bad news. Yes, in fact, BASF is a plastic producer, and we have a lot of trouble with plastics in the environment, and this needs to be changed. And we will not reinvent the wheel today, but we will help to make it really circular. And this is like how we imagine this. Today, we have a very linear environment, a very linear plastic industry. Plastic is produced, consumed, and wasted. Typically wasted in the majority around the world, it's in landfill and littering. And we are happy if it lands not in the ocean, but it's under control conditions. For us, the next step is, can we reduce this amount and use at least the energy? That's the second step. And now it comes to what we are looking for. It's like, can we close the loop? So is it possible for us to recycle plastic, not only in energy recycling? So how can we use this by taking a reuse of the material? And then from our perspective, is the first step is recycle mechanically from plastic what is possible to recycle mechanically. And the second step is, can we, those fractions which are not longer mechanically recyclable, can you recycle them chemically? But honestly speaking, we have to be here aware that the recycling quota of mechanical recycling is not 100%. So I think it's around 90, 80, 70% of that material which is pure enough. The chemical recycling is not better than that. So as I told you before, if you do a chemically recycling from plastics, and we are talking about polymers here, you have to start, and now coming back to square one, you have to get back from polymers, from plastics, back to chemicals, and probably back to crude naphtha. So if you remember my presentation beginning, it's like we normally have energy-rich starting material, and we are consuming the energy of that material. We now have an energy-pure material in forms of plastics. So whenever you start chemically recycling, you have to refuel that energy. And that is the biggest challenge we have today. So if we are coming back from plastics, refuel the energy, and we are talking about a quota of 20,000 tons. And this alone is already really challenging to be refueled. And once this is done, for example, with our investment in companies like Quantafuel, which develop those pyrolysis technologies and those chemical recycling technologies, Once this is done, we have to refuel this into our chemical value chains. And that's what I show on the map. That's a pretty much last slide today. It's like we are using crude oil today. We are using this in our heart of our production structures, which is the steam cracker, which is producing basic organic chemicals. And then we start the production along 2, 3, 4 steps to get a product, today fossil. What our target is we like to use recycled material. We produce a kind of naphtha, which is very similar to natural or fossil naphtha. And this is then introduced directly at the beginning of our value chains. This is the same. What you see is you have basic organic chemicals produced of that, and you will end up with a typical product, which is chemically identical as the pre-run fossil product. This is extremely important for our customers. Told you before, the volumes we are operating, we are forced to maintain the quality and the specification of that material throughout the years. So this is for us the most elegant and most easiest way how we can guarantee that our products do not change their behavior. They still stay the same, but they are now from a more and more recycled share produced. But this is, as also mentioned before, this is not for free. Refueling recycled material with energy, collecting and breaking it down to a kind of naphtha starting material for us is costly. This is more costly than the typical oil. So we have to allocate the costs to those customers who want to buy that material. So yes, again, Michael, you mentioned that quite nicely before. The products will be more expensive than oil-based. But also what our observation is, our customers are more and more aware of that, and there is a certain price premium possible. So this is done by allocation. This allocation is done by a third party so that we cannot double count recycled material to a single product. And it is also for us very important that whenever we introduce a recycled material into our Verbund, that the net sustainability values, for example, global greenhouse gas, pollution, and so on, are not negatively influenced. So this is why every of our, let's say, chem cycling and mass balance approaches are accompanied by a life cycle analysis and an assessment to them. This is what we do, for example, in-house. And I think, Lars, you also mentioned in your presentation that our values are quite transparent and that you can, let's say, they are publishable, they are transparent, and they are, of course, open for discussion. So with this, I would like to end my presentation. Sitting in Gothenburg, specialist for renewables and for circular materials. I would like to thank you for your attention.
Thank you very much, René. Sorry. Interesting. BASF is a company I've followed for a very long time. I think I visited Ludwigshafen the first time in 1977 or something like that. And I understand a lot has happened, but when you look at it from above, as in your picture, it looks the same. You have to come closer. A question here. You mentioned, the customers who wants to pay for it, do you have customers who like to pay the extra money for this? Or will you have it?
Of course. Unfortunately, it's not everybody. And this is as well as with our initiative on chem cycling, we have to be a little bit more careful here, because the requests we get after publishing that we have material available, the requests are strongly increasing. So we are not able to double sell. So this is something where we have to be very careful how we serve these upcoming markets. But that's, it's nice to see that customers are willing to pay.
What is your future plans for chemical recycling, for example? How does it look? How are you going to expand into that area heavily, or how do you look at it?
I will not take any global statement for BASF today, but I'm very sure you can expect that BASF will set a volume target or a sales target like Solvay, for example, is setting, that we will, of course, try to develop this market further. Especially, but let's put it that way. If you're talking about waste materials, BASF will never be a waste company. We are a chemical company, so we would like to see a supplier scene similar to the fossil supply, supplier environment coming up based on raw material, based on, let's say, recycled waste.
There's been a lot of information now, and maybe I'm totally wrong on this, but can we say that the chemical recycling is more about avoiding littering than to avoid CO2, GHG emissions? Is it so?
No, it goes hand in hand, I would say. Littering is one thing. We are clearly aware that plastics have their demand. You need plastics for functionality. But then you also have to you need the responsibility to use the litter as new feedstock. Yeah, that's for one thing. But on the other hand, we can also, and this is done in our life cycle assessment quite openly, we can also show that they lead to a reduced CO2 footprint, or greenhouse gas footprint. And then we also have to indicate, yes, we do not consume more oil than necessary and can save oil for really things which are not accessible from plastic or from waste today. So this is like, yes, it has more than one benefit to reduce plastic waste.
Okay. And what about, since I'm today representing the Nordic Bioplastic Association, what about the BASF and the Bioplastics? What's happening there?
Bioplastics, you mean plastics biodegradable, or do you
mean bioplastics from renewable sources, if you say, like, put it like that? Yes.
Okay, I will not show the slide, but I think it cannot be only recycled way. This is not possible. For chemical recycling today, we are using a specified stream of, let's say, more polyethylene, polypropylene based compounds, and not polyamides and polyvinyl chlorides. This is not possible for chemical recycling now. And by doing chemical recycling, you're losing 20 to 30 to 40% of material in the recycling process. So if you're honest with yourself, you see you can recycle twice or three or maximum 4 times, and then the material is consumed. And this material we have to replace. And it would make sense to use bio-based material to replace those materials we cannot recycle by chemical recycling any longer. But this is exactly like, this will not come by tomorrow. The chemical industry now is 150 years old and optimized on oil. So let's see how we can transform this gradually into a kind of bio-based and recycled-based industry.
Yes, I think it's Ellen MacArthur, the foundation, that said that there should not come out any new fossil-based plastic on the market, actually. And if we need to, of course, to put in some new polymers, but they must be from bio-based material then. Is that possible in the future?
Yeah, I hope. Today, I would say we have a time in front of us where we have a mixture, a blended mixture from fossil, recycled, and bio-based materials in front of us. And then let's see how this can develop, how we can increase the share of bio. But this is future. I'm very careful to give any statement about how fast this is possible, because we are talking about huge demands in volume and huge demands in energy. And this, if you look at biomass, this is full of oxygen. You need much more energy to convert this into a feedstock for the chemical industry for plastics. And this has to be taken care about as well.
All right. Okay. Let's see. I'm not sure if we had any questions for you. Yeah, well, there is one from Graham Smith from Monday, I think. How do you allocate the green credits in the mass balance calculation? Is this by a chain of custody or traceability? What are the boundaries of your system? Material grade, type, site, country? Do you follow it?
Well, I'm not 100% expert in mass balance and traceability. Chain of custody is one thing, But of course, we need to listen to our customers, what is more important for them. And I might have the idea that traceability is much more important than chain of custody. And this is something where it's like, yeah, let's see. I will not interfere with the regulatory here. This is under discussion. But yes, of course, for us, customer is king, and and honestly, we are all kind of green inside. We need to, that's what I see in the community. The whole community wants to do something right. Yes. And then it's like, how can we perform this, and how can we self-confident that? And
Michael likes to add something here, I can see.
Yeah, with the mass balance approach, I think we have existing sustainability certification systems like ISCC or RSB. They include already very solid mass balance standards. And at the moment, there is an ISO standard for mass balance approaches under development. There was a different workshop on that, and we can expect perhaps this year an official ISO standard how to do mass balance in detail.
We have another question from Graham here. Will the EC define and allow chemical recycled material as recycled content for future packaging solution and use it in the Green Deal?
Don't
Who
know.
wants to answer?
Michael, maybe you're better at that, because this is ongoing discussions.
He's the perfect kickback.
I tried to gave already an answer, and we had a good meeting with the Commission last week, and it's under development, and there are some very important questions. I think they will decide that a life cycle assessment and the carbon footprint will decide whether you're counting the recycling quota or not. So I have the feeling they will do it technology open, but they have, of course, to define in detail the rules to make the LCA in a proper way. And this is what they're doing at the moment. But it seems so that they really are technology open, and this is very important for a new technology.
And then we take the last question from Graham. Then I think we don't have more time. Are there concerns about greenwashing if traceability is the direction we take?
Well, there will be always people who claim greenwashing, but I can assure you this is not our interest. What we do with a clear statement, and we want to change, and we want to shift our raw material base to something more sustainable. And greenwashing is nothing for us.
Okay.
I think that's yeah. We will take care that there will be no reasonable claim possible to have greenwashing to us. It's in own interest.
Okay, friends, I think we are done for today. It's been very interesting from all three of you. A lot of good information. I hope the listeners appreciate it too. I'm sure they do. We will, of course, come back with new webinars, and we will, of course, use Nova Institute again, because you've done an excellent job, and maybe we come back to you also. BASF, you've done an excellent job too. But when this happens, I don't know yet. We haven't come so far in the planning, so the time frame is not sure yet, but we will do more. Michael has something more to say. Yes.
One very short comment. We have missed in our presentations to say that we have an extra workshop on chemical recycling with the European Commission, with German Umweltbundesamt, with VTT on the 10th of February. And I have posted this in the chat here and in some answers. So please, it will be an exciting day, not only have presentations, but discuss with the Commission the questions we discussed today here. And it's on 10th February.
Okay, thank you very much. There was a question in the beginning also. Will it be possible to have the presentations? I'm sure that Nova had no problem. I don't know BASF, it's more sensitive with the big companies, I know that, but can you, if it's a problem, can you sort of adjust your presentation and make it as a PDF and give it to us?
Yeah, that could be possible.
Then we will make sure that you get it, you who has been listening here, that you will get it one way or another. Maybe that we will put it up on the Nordic Bioplastics website, but we'll let you know, and there you can download it. All this has also been recorded, so I think we can maybe save the file somewhere also, so you can listen to it again if you like to. So I would like to say thank you to all of you for a very good job, and for all people who's been listening. And I hope we will meet again soon, and maybe that we can meet for real and not just only on the screen, because we are longing for that, I think.
Yeah.
So
thank you very much.
Yeah, take care, everyone. Stay safe.
Yeah. Thanks.
Bye.
Bye.
Okay.